Hey everybody, this video is going to cover how to do some basic t-tests and correlations in R. So you should have already watched the lecture on these topics, and really getting a little bit more into inferential statistics and the application of them. Because the lecture sort of ends with a rant on null hypothesis testing, and doesn't really cover like, okay, so I can tell you a single sample t-test is one group of people, but how does that end up working out realistically? So I'm going back to that same basics data file that I was using before, and I'm going to set my working directory, which allows me to set a specific number, a specific place to look for my data. Now I already have it saved in my file, but you're going to want to set yours to your own because this will not work for you. That's mine. So go to Session, Set Working Directory, and choose the directory that has all the files that you've downloaded from Blackboard. Once I do that, it should come up here, down here where it says console. And what I can do, if yours hopefully is not as long as mine, click this little arrow right here, and that will bring up all the files that you have in that folder. So I can see that I have all these CSVs, and we're going to use some of those today. We're not really going to use this basics ones or this chi-square one, so I'm just going to turn those off. You can load them if you'd like, but we're not going to use them in this example. I think I have chi-square at the very bottom of this, but we're going to set chi-square aside and do it in a bigger module where you can learn a bunch of different types of chi-square. Okay. So let's actually I'm going to go ahead and get rid of that chi-square stuff, and we'll stick it in another place. Okay. So as we go here, I'm going to update this just a little bit with some tricks that I've learned. So one thing you can do is put 4 pound symbols around your text that you're wanting to just make notes to yourself, and that actually will bring them up in a little kind of an outline down here at the bottom. So you see, as we go, we can add more. So let's load all these data sets. I've got them called choral data, dependent T, independent T, and single T. And because I've set my working directory, that allows me to just load them all at once, instead of clicking import dataset from file and doing that over and over and over again. So I really want you to get in the habit of using this working directory and then having the file name imported, saved at the top, because then if you send me your code and you're trying to figure out like what's going wrong with somewhere, I can see that you've imported the data and they've been imported the right data. Whereas if you send me your code and you've done this import dataset clicking and don't save it at the top, I can't tell totally what's going on. So let's say you have the names of a problem. The name of a data set is a problem, if I can talk. So let's just say you are on a Windows machine. And so see, I added those columns down, and now it's popped up down here. And for some reason, the name of the column, the first column, has gotten eaten somewhere. You can fix that. So remember, we talked about this in the last video. It can change the column names to something else. You can actually change all of the column names. It's just an example of changing the names. Don't actually make it cheese because we're going to need it to be feminine later. But I can fix any problems with the import that happens. Alright, so we've done all of this. I'm going to skip past all of this stuff. I'm going to put a little label here. This is where we did descriptives. And I'm going to skip all of this because we've actually done this for the last video. Now let's go down to single sample T here. And one nice thing about having these little markers is when your code gets to be hundreds of lines long, it's really convenient to help find things. So in a single sample T test, you're going to have one column of data. So I'm going to click on my data set over here, and I have this one column of data that's got 15 data points. It's still listed as a data frame because it's here under data instead of a single vector, but that actually doesn't matter. Okay. So I'm going to close this. Let's go and look at the example here. So the example is that we have a school that is claiming that their honors gifted program is significantly better than the national average. So if I have the national average of an honors gifted program as 1250, is their claim substantiated? So let's go back over here and look. The way that you do this is that you take that column of data and test it against your known data point. So back to what is single sample t? Well, single sample t is when you have one group of people or one column of data and you test them against a single number. So a known population number. So this is really useful if you are testing this kind of scenario where I want to see if one group is different from some national average. And for some reason, I don't have the standard deviation. Okay. So the way I'm going to do this is the t.test function. T.test is a really great function because it actually will work for all of the functions, all of the t-tests we're going to use. So you really have to know which one you're wanting to run so you know which of the options to use. So in t.test here, there's two options for a single sample t. So I'm going to make some notes as we go here. So single sample t requires two parts. The column and then mu. Oops, not me, mu. Okay. So we've got the column here. So the data set is single t. The column name is SAT score. And if you're typing along, remember, it'll come up and give you that option to type the column. So this allows you to pick one column out of a larger data set as well. I'm going to type comma. Mu. Mu stands for population mean. Mu is the Greek symbol for that. It's a little curly U. And I put in 1250 because the example here said that it should be 1250. Okay. And so I would run that. And what it's going to give me is some output to interpret here. See if I can make this bigger. There we go. Okay, this is like getting to be too big on my screen, but hopefully you can read it. So it tells me what data I used, and it gives me all the numbers I need essentially right here. So I've got my t score. So this is the ratio of good variance to bad variance. So it's 4:1. It's a pretty good ratio. Gives me my degrees of freedom. I don't think we've talked about degrees of freedom yet. So what the heck are degrees of freedom? Degrees of freedom are the number of data points that are free to vary, which is probably the most oblique, sort of obfuscated definition of something you've heard. And so really the technical definition of degrees of freedom is it's the number of scores that you have minus the number of scores that you had to calculate to get to that point. So I had to calculate the mean, so it's -1. But that still also doesn't make sense. So the way I think about degrees of freedom is it's the number of scores that I could change, so the free to vary part, and keep the same mean. So I can change all but one score and keep the same mean for my sample. So I can move some numbers around, make some bigger, make some smaller, but I would have to have at least one of them at the end that is stable or a certain number to make the mean be 1370. Degrees of freedom also is sort of, it's an estimate of, not power, but it's an estimate of like, what's the word I'm looking for here? Sort of how much, I guess power is the only word I can come up with here, you had in your study, meaning that the larger the sample, the more believable I find your study. Because remember, small samples can have outliers, they can have weird people, but larger samples tend to be more consistent because of the central limit theorem. So as we get larger and larger samples, the data sort of settles out, it becomes more normal, it becomes the standard deviation, standard error tend to decrease, and just kind of the law of large numbers, that the more people that you have in a study, the less impact any one person has, and the numbers sort of become more consistent. But technical definition of degrees of freedom is the number of scores that are free to vary. And the formula is generally n-1. And that's not something that totally really matters right now, but just kind of a reminder from basic stats, since we haven't talked about it in the lecture. Now I also got my p-value here. So this is the actual p. Remember, it's not alpha. It's the probability of getting this t value. We've set our criterion at p less than 0.05, which is our common alpha number. Right? So we want p to be less than 0.05. So we're setting type 1 error at 0.05. Our p-value is less than 0.05, so we would reject the null. Okay. So we would say that their score is different from 1250. And what that means is that their score is higher than 1250 because here's the mean. So their average score is 1370, which appears to be higher than 1250. So what do I do with all that information? I've got the example of the write-up over here. So we've got the mean listed. We'd have to calculate the standard deviation. So let's do that. That's this next line down. So this code from our basics lecture. So column na.rm in case you have missing values. And so standard deviation is 112.68. So that's where I got this number from. Here I've taken this t stays. Here are the degrees of freedom. If you're writing in AMA format, American Medical Association, these degrees of freedom sometimes are in subscript without the parentheses. This is APA format I've got listed. All right, and I've done everything in 2 decimals except P, because P you can get away with 3. I've listed the T degrees of freedom and then the actual T value, okay, in this format. Our P value, which is I said equal to 0.001, because it's not less than 0.001, it's equal to 0.001. And then I listed the effect size, so this is Cohen's d. So how do we get that effect size? Well, what you do, and we're going to add this, I'm going to add this code in, is we're going to calculate that using some effect size scripts that I have written. So let me zoom out just a little bit so it's not so big. I think okay, that's fine. So I'm going to open a effect size script. This is on Blackboard, and you should download it. I have mine hidden a couple folders. This folder. And this is a scary looking file, so let me zoom out. It has got just tons of stuff in it, and it has a whole lot of stuff. Don't edit this file. Hit Control A, or if you're on a Mac, Command A, and run the whole thing. Now the bad thing is that we have not been able to make this into a package yet because life is crazy sometimes and I've been busy. But one day this will be a package and we won't have to do this. But once you run the whole thing, you'll get all this extra stuff out here. So this script will work for lots of different things that we're going to do this semester. So you're going to use this F size thing a lot. So I'm going to come back over here to basics. And I'm going to start typing d dot, and I can actually hit tab and get a bunch of, the options that I have here. So I can do D for dependent T, D for independent T, or D for single T. So I want this regular single T one. And the nice thing is that it pops up all of the options that you should type in. Okay. So I am going to do mean equals, well, what was our mean? Let me rerun this so we can get this back down at the bottom. The mean was 1370. Okay. And then we've got our standard deviation. Well, we just figured that out. Standard deviation was 12, this number, 1268. Okay. What else do we need? We need n. And I have the length function here. But remember, we talked about the length function. We need to add this NA omit thing, just in case there are some NAs in our data. So I have 15 data points. The other thing I can remember is that degrees of freedom is 14, so that makes n 15 because it's n plus 1. The other things that we can set in this function are alpha. We set it to 0.05, so remember alpha is different than actual p, so don't write your actual p value here. Alpha is what your criterion is, and we're going to use p less than 0.05 all year. And k is the number of decimals. Why k? I don't know, I just liked k. And those are the basic rules for a single sample t-test. Okay. Now, that ran fine. It gave me a bunch of warnings. This warnings thing is okay, so I could look at those, but it's just going to tell me that it didn't get full precision. What that means is that the function ran, it didn't settle very well because I clearly forgot a number here. Okay. And so I think what it did was it compared everything to 0. Because look here, our t value that it gave me did not match. So I can even remember my own function. So what are we missing here? mu. So I'm going to add that here, was 1250. So rarely do a single sample t-test. The other thing that you can do is that I actually have this, and I should have done this myself, is open this calculate.r, and it actually gives you examples of every single one. So I should have started here, single sample t from means, and I could have seen right here that I had forgotten mu. Okay. But the nice thing about doing this, let's go back to my basics here, is that I looked at my t value here that I got in the output, and it does not match the t value that I got in my test, and so I know I've done something wrong. Okay, let's try that again, this time with all the right numbers. Okay. Couple little warning messages, that's okay, but this time I got numbers that I was expecting. Okay. So the nice thing about this data here, let's paste this over here, is that it's an APA style. Okay, it didn't copy quite right, but look, I've got the same mean, standard deviations. I can't make the italics happen in R. It gives me standard error as well, a 95% confidence interval for the mean. Okay. And so that's how much the scores vary around the mean, plus or minus about 2 standard errors. Okay, so it's about plus and minus 60 points on each side. And then it gave me my t-value, again in APA style. So if you aren't quite sure how it's supposed to look, you can use the output from this package. Now, I would have said p equals 0.001 because that is a little more precise than p less than 0.01, but that's also true. The big thing here is the d equals 1.06. That means that it's a large effect size because this is made up data. And so they're at least, the two groups are pretty far apart. This confidence interval here is the confidence interval on d. So how much our effect size varies. And we haven't totally gotten into what confidence intervals are either, so let me give you just a brief explanation. So confidence interval is a range around a point estimate. It could be the mean, or here, the one I've highlighted is a range around Cohen's d. And there's a lot of controversy about confidence intervals right now on what they actually mean. Because technically the definition of a null hypothesis testing confidence interval is that it's an interval that 95% of the time should contain the true population mean. Okay. And that is just kind of a mess because we don't often believe the null is true, right, from the last video. And so there's some yap about what they actually mean, but the way I think about them is that they are a range of believable scores. So the way a confidence interval is calculated is that you have the point estimate here, so 1.06, or in this example, the 13, and you calculate a range around that contains 95% of the data. Okay. And that is usually calculated by adding and subtracting about 2 standard errors. Okay. It's not always perfectly 2. It depends on how many data points that you have, and depends on how many data points you have, but 2 is a general good number to know. And so that gives me, like I said, for this one, about plus minus 60. So you see that it's 50, I can't math today, that's 53 points up and down. But about plus and minus 60. These are non-central confidence intervals, which is a whole nother ball of wax that I don't want to get into, but you get the basic idea. It's about plus or minus 2 standard errors. What does that do for me? Well, that gives me a range of precision. So I can look at a confidence interval and say, well, they got 1370 this time, but really the range of scores that I should believe for this sample is about 1300 to 1432, because nothing is ever precise, especially when dealing with people. And so the range of believable scores is between these two values. That's really helpful for effect sizes, because now I can tell that the range of believable effects is somewhere between about a medium, remember 0.5 is medium, to large. So this effect is a medium to large, that's still pretty big. And I would say, well, yeah, their scores are different from the national average. Okay. So confidence intervals, the way to think about them is a range of precision. So it's about 2 standard errors on each side, and it tells me just like kind of, I always think about it like, what are the scores that I should believe given for this study? That's really handy because having one number doesn't always tell you the most information. So it's kind of the same conversation we had about standard deviations, except now we've made them into this interval range. Instead of just talking about plus and minus 1 standard deviation, now we're using plus and minus 2 standard errors. So this is supposed to be about the population, so we're using standard error instead of standard deviation. Okay. All right, so all that's a single sample t-test. How often are you going to use that? Not very, because single sample t is not, generally your studies are a little more complicated than that. So, but we will use dependent t a whole lot, especially when we get into repeated measures ANOVA, because it's sort of a follow-up test to repeated measures ANOVA. So let's talk about dependent t next. So dependent t is where I have one group tested twice. And we're going to do a pre-test, post-test design because that's the most common thing that you'll see. But I might be comparing 2 different ratings from one group, or they took 2 tests, which test did they do better on? There are lots of examples. So this is a cheesy example from a intro stats textbook where I measure their belief in the supernatural before and after some science fiction movie. And then I would see if they were less likely to believe in the supernatural after watching the movie. Okay. So I'm expecting their scores to go down, but we're just going to test their scores, see if they change at all. Okay, so let's come back over here. Now, dependent t is a tricky pain. So one issue, and then I'll make this big again so you can see a little better. One issue with data sets that are repeated measures. Okay, so I'm going to click on dependent t over here to show you what it looks like. And generally data sets are formatted such that each row is 1 participant, which is fine. That's the way you probably should do it. But the issue with that is like you can't always use the functions you want where they're laid out in what's called long format, or wide format here. Sorry, this is wide format. And so what that means is that each person has their own row and each column is something about them. Now, sometimes that means we have to change this format. When we're doing correlations, you don't change that format, so it depends on the type of analysis. But for dependent t, we do have to change this format. Okay. And actually, I don't think we do, but I'm prepping you for the future. So you'll use this function a lot, so we're going to talk about it now. So what we're going to do is you're going to need to install the Reshape library if you haven't already. So you're going to click on Packages, Install, Reshape. Do not use Reshape 2. There's 2 of them. Just Reshape singular because Reshape 2 is different. Okay. Then you'd click Install, make sure you have it. I already have it. After you install that package, we're going to open that library, which is not normally a controversial thing I ask my computer to do. All right. So I may have to crash R here for a second, but let's see. I do have both reshapes and I only want this one. All right, 2 seconds while I restart my R because apparently I have done something that has made it mad. All right, take 2 with the Reshape library suddenly just loaded itself, so let's talk about what does Reshape do this time. And anytime you have that where, as you saw at the end of the video, where it wasn't giving you the little arrows next to it, that usually means that it's still processing. You'll often get a little stop right here, or that it's just stopped working. And that happens every once in a while, and so oftentimes you will have to completely crash the program and reload everything. It will reload most of what you still have open though, but always save if you can. So that's the nice thing about using RStudio, is that every once in a while it just gets cranky and crashes on you, but it will open to have most of what you had open before. Okay, so back to Reshape. So we have everything here in wide format, and what wide format does for me is that it has each person has their own row. Great. However, most of the functions we're going to use for t.test and ANOVA require the data be in long format. So long format is where each data point gets its own row. So I need a participant ones before data point, participant ones after data point. So if I could, in a perfect world, edit right here in this window, I would cut and paste this after column here and stick it whoop, right here on the bottom beneath the before column. And then I would tag each one as before and after. Okay. So what we're going to do is create that data set. So go from wide to long. And one thing I'm going to do real quick that I don't have here is add a participant number. So I'm going to do dependent t part no. So I'm creating a column right now. So this is something we haven't done except in the intro to R piece, is create myself a new column. And you don't actually have to do this for dependent t. It does not require it. However, this is something we'll do more later, so I'm going to add it in. Okay, so I'm going to take it, I'm going to add a participant number, and I'm just going to say 1 to the end of dependent t. So I'm going to say 1 to length, my dependent t before column. Okay. The other thing that you can do, I think the way I usually do it, is in row dependent t. So I can do it either way. What does in row do for me? It tells me how many rows are in this particular one. So remember that the colon counts up by ones. Okay, so that's going to count, oops, sorry, see down here, 1, 2, 3, 4, 5, 6, 7. So I'll run that. So what does that do? Well, I added a column with a participant number. Okay, and that's really handy so that I can match up people. All right, now this melt function. The way that we're going to go from wide to long is called melt. And what melt does is that it takes wide data and melts it down. So it's actually a convenient name because you're sort of taking a wider data set and melting it into a longer data set. Okay. And so the way the melt function works, and actually just let me kind of hide this real quick and we'll type it out as we go. So dependent t, I'm going to make up a data set name, long. I always put long afterwards so I can remember which one it is. Do not overwrite the original in case you screw it up. Okay, so call it something new. Is melt. Melt is the function name, so open parentheses. The first thing you're going to type in is the name of the original data set, dependent t. I'm going to use my ID variable. So an ID variable is anything that isn't changing. So any of the columns that you're using that aren't going to change. So that's going to be part no. Now this has to be in quotes because it's text. That's one of the harder things to get in R is when is it quoted and when is it not. If it's got the $, no quotes. If it doesn't have the $, it probably needs quotes. And what that is that column is not going to change. So it needs to stay, and what's going to happen is it's going to repeat. So it's going to take that column, it's going to leave it there, and repeat it twice. And then measured are our repeated measured columns, and those are the ones that need to get melted. So ID columns are going to stay and get repeated. Measured columns are going to get melted, meaning they're going to get moved from being next to each other to one below each other. Okay. And that's what I was talking about, taking this after column and sticking it right here down at the bottom. I'm going to use the C function because I've got more than one. So I'm going to do before and after. Okay. Now, everything you type here in quotes has to match over here. So if you type in the name of something over here that is not over here, it will be grumpy with you. Or heaven help me, sometimes melt does nothing. It just is like, okay, whatever. And you'll have a data set that you think ran and it's a hot mess. So until you get used to using melt, I tell you to always check, make sure you did it right. I am stacking my code when you get to graphs, we'll talk a whole lot more about stacking. And that just makes it easier for me to see. So I've got all 3 pieces I need. So if you don't quite get why I hit enter after each comma, go with me and then watch the graphs video, and I'll talk about this a lot more, stacking your code. It also makes it easier to read and debug when you make a mistake. Okay, so I ran all of those, and now over here I have this dependent Tlong. So I'm going to click on that and I'm going to show you the difference of what happened here. So this is what we had before. We had before and after, and we added a participant number. This is what we have now. That participant number got repeated. So 1 through 7, 1 through 7, I can sort. Anytime you sort over here, it does not actually do anything to the data set. So I've got 2 rows for 1. It created this new column called variable. Variable is the column names from before. So it took these 2 column names and stuck them here. So that's the original column name. And then value. Value is the number that was in the column. So this is basically IV and DV. So they called it variable and value. And every time you use melt, it will call them variable and value, which is a little annoying. So we're going to change that and call them something else. I have no idea what I am doing here, so we're just gonna get rid of all of that. I think I did a second example, I guess, in my last class, and I don't know what all that mess is. So we're going to change the name of the columns is what's happening next. Doing this on the fly, can you tell? So I have my dependent Tlong, and then column names are participant number, variable, and value. I want something else. So let's use the call names function. So call names, dependent Tlong equal. You'll notice I put no brackets there because I want to do all of them. I want part no to stay the same. And then I want it not to be variable. What can we call this? Time, because it is the time point at which we measure them. And their score, their belief in the supernatural score. So what did that do? I'm going to click here. And it changed that from variable and value to time and score. Okay. All right, so now let's actually run that dependent T. So it's t.test, it's the same function. And what we're going to do is use this tilde format, which is dv tilde iv. So the tilde is above the on my keyboard, it's the leftmost one. It's not the one, it's the little tick mark thing is above this one. So it's this function, or that symbol. And what I'm going to do is do the dv first. So dv first, dependent Tlong, dv. So it's score, tilde, iv, dependent Tlong, time. So that should be dependent variable, tilde, independent variable, or dependent variable, tilde, group. Now, we have to add a couple more little things here. So we're going to do paired equals true, because it is a paired t-test, or a dependent t-test. And I'm going to add this little piece of code right here, var.equal equals true. It actually doesn't do anything for this particular test, but it does allow us to remember to do it on the next test. So this does nothing here, and it seems weird for me to tell you to add some code that does nothing, but it's so that I never forget it for the next one down, because I'm a forgetful squirrel. Okay. So paired equals true is the main thing. This really has to happen because dependent T. Okay. All right, so let's run that. So what we've got now is our paired t-test output down here at the bottom. So let's make this a little bigger. It gives me my t value, my degrees of freedom. So it's 6 because I had 7 data points minus 1, and my p-value. And so I would say that this is not significant because a ratio of 1.5 to 1 is not really that different. It's almost a 1-to-1 ratio. This confidence interval is a confidence interval of the mean difference down here. So here's our mean difference score. So their scores changed about 1 point. But at the moment, I don't really know what that means. Do they go up 1 point or do they go down 1 point? So we're going to look at the means. So here's a scenario we haven't had. We've used the summary function to look at the means for a data frame, and I can do that. So I can do summary of my original data frame, and I can look at the mean for before and the mean for after. So their scores are going down 1 point from before to after. But I haven't really had this scenario where I have to get a set of means based on having a grouping column. So here I have this group column, and so I need the means based on these groups. I want the mean for just before and the mean for just after, but before and after is in a separate column. Now, I could go from long to wide format, but that is an evil function called cast that we just don't want to use. It always makes me think of like Dungeons and Dragons, but it's gross. So let's use the tapply function. Okay. So the apply function allows me to calculate, if I can find the open parentheses, the apply function allows me to calculate different mean, standard deviations, or whatever across columns or across rows. Tapply stands for table apply. That allows me to calculate functions based on groups. So if you're trying to get when do I use apply, when do I use tapply, T applies for groups, applies for rows and columns. Okay, there's even more of them. There's S, L, and M apply as well. We're going to use apply and tapply. So tapply is in the same format of dv, comma, iv, just like it's dv tilde iv here. So we're going to do the same thing. Dependent t long, our dependent variable, score, split by this specific group. So we're going to split by time, and then the name of the function, mean. If you want to get really fancy, you can also do this. Because remember, when we did our mean function, it always had na.rm, so it would take out those nas. And so now I can get the means for just before and just after, which thankfully match the means up here. Okay, but now I have more precision. Then I can do that exact same code, so I'm going to copy this, paste it here, and here, instead of saying mean, do SD to get the standard deviations for each group, which is how I have the means and standard deviations over here. But we're really working towards how do I get this dependent t average score. So let's do that subscript here. So how did I get this d value over here? That's where I'm headed. So now I have my means and my standard deviations. We're going to do one more thing. And type in length here. Now length does not have this na.rm, so I'm going to take that out. Okay. And run that. So length here is 7, so there are 7 people in each group. Or 7 points in each group. There's 7 people total, because remember this is a dependent t-test, so each person's tested twice, so these 7 people are the same for each one. Okay. Which is really just how many rows are there in dependent t. Now one trick that I taught my students last semester is I can actually save all of these things. So I can call this mean stdv. It is very tempting to call this sd. Do not do that. That's the name of the function sd. So call it something other than the function name, because otherwise you'll have a miserable existence later, because I have done that by accident. So don't do it. So I'm going to save them. What does saving them get me that just letting it show me the output didn't get me? So now I'm going to do this. So I've got mean, SD, and N all in one row with some semicolons in the middle, and it outputs it in this like nice pretty format where one column here is for each variable. So I've got before's mean, standard deviation, and it's 7 people in each one. But after's mean, standard deviation. Okay. What does that do for me? That allows me to calculate my effect size just a little bit easier, because I can see all the numbers kind of all at once. You can do this either way, whatever floats your boat, but I have heard from students that this format is nicer to view. All right, So we're going to do, there's two options here. There's dependent t average and dependent t differences. We're going to use dependent t average pretty much all semester. What is the difference between them? It's all about the denominator. So dependent t's calculation for Cohen's d is time 1 minus time 2 on the top. So the numerator doesn't change between the two. The denominator is either an average standard deviation, so that's dependent t averages, or the standard deviation of the difference scores, so that's dependent t differences. There's a lot of people who say that dependent t averages is a better estimate of the effect size because dependent t differences overestimates. And so that could get into another whole can of worms, so I'm going to take my word for it, and we're going to use averages. So I'm going to type in all the numbers I need here. So I got mean 1 equals, and I got 5.57. So this is the slow part, is you do have to type all this yourself. And you can type it in any order you want. So I'm going to go all the way down. So 1.99, and n equals 7. Oops, that's going to need a comma, or it's going to be really unhappy with me. So I got mean 2 equals 4.43. SD2 equals, don't define SD1 twice, 2.88. N is still 7 because there's only one n here. Alpha is 0.05, k equals 2. Okay. I could have typed that mean 1, mean 2, SD1, SD2, so you can type them in any order you would like. Okay. Now, this gave me a bunch of numbers here. Stick that here and see if it matches what we have. It probably does not match the d value because this is probably not the right one that I'm telling you now to calculate. Oh, that copied really poorly. Let's hit enter so we can see where everything is. There we go. Okay, so give me my mean 1, my before mean, and standard deviation. Now I also have standard error. I give me my mean 2. Standard error. Now my d value here is 0.47, and that is because the d value I had in the notes here is probably d differences, so they're going to be different scores. But let's go with the average, and then watch this note here. So the code here outputs a warning or a note that it's not going to show you the t-test or the p-values because they are not calculated. Like, I can't calculate the correct one, so I can't really check and make sure my t value is correct, but I can make sure I entered my means right, but the t and p values are not going to match the output because the denominator is different. But what does that tell me? The size is medium. Oops, this version's bigger. Okay, this effect size is medium, but the range of plausible values for that effect size ranges from something negative to something positive, which means that 0 is a plausible number here. So this effect is not significant, and the range of plausible scores includes 0. So I would say there's no change in scores. Now I wrote this up just like the last time in APA style. So t, my degrees of freedom is 6. My t value is 1.43, p value is 0.2. And I got that from the t-test output, which if you don't want to like scroll through all this stuff that we've done, just run it again. Okay. And so here's my t, my degrees of freedom, and my p-value. So that's a lot of work for dependent t, but I promise that's the one that requires the most typing. Okay, so that's dependent t. Let's try independent t. So independent t is where I have two totally separate groups of people. And in this case, we're hypnotizing people and then seeing if they remember stuff better in this mock robbery scenario. And so we really do not have enough people for this to be a powerful test. But this is just an example. So are people who are hypnotized better than not? Okay. So let's code, let's code this here so we get it separated out. Now the nice thing about independent t is that it's already in long format. So independent t has which group they're in and how many questions they got correct. Now one thing I haven't done is I haven't given them group labels. Okay. So one nice thing that I should do for myself is like label which group is which, because that would be helpful. So let's see, the 4 people in the experimental group that were hypnotized are probably the first group here. 1, 2, 3, 4, right? So 14, 12. Okay, so it looks like group 1 is the hypnotized group, and group 2 is the control group. So let's give those groups some labels. This is another command we're going to use a whole lot this semester, which is the factor command. So I'm going to do independent t group. So we're gonna fix this column. We're gonna factor it. So the factor command works by first listing the column that you want to factor. So what do I mean by factor? I mean give them labels. Okay. So I've listed the column name, so it's this name and this name match. Okay. I will say the levels equals. Okay. So levels command is just something that is like, what are the levels? So what is currently in the column? So whatever you type here under levels has to be in this column, or you're going to wipe your data out. And you will do this at least once. It's okay. It's normal. Okay. And so the levels are currently 1 and 2. In the next data set, they might be 0 and 8. And then the next data set, it might already be like A and B. So this being 1 and 2 is not always true. Okay, what is actually in the column that you're working with? Okay. And then I want to give them labels. Oops, helps if you spell labels correctly. Okay. So labels here, remember I use the C command because you have more than one thing. Labels is what do you want to call 1 and what do you want to call 2. So I'm going to call that experimental group and control group. So this is a space where you can use spaces because they're labels. And so that's about the only time that you can use spaces. Okay. All right, so what is that going to do? So here, it's 1 and 2. Let's see what happens after we run this. Go back. Now they have labels. Over here, when I click the little down arrow, it says that the group variable is factored with 2 levels. So the factor command actually creates a factored variable. So it doesn't just give them text and change it to a text column, because remember you can have character columns. It actually codes it as factored. So if you've used SPSS before, this is like adding value labels to a column. All right, so the way independent t works is basically the same as dependent t, except for this one line here. Okay. So it's dv tilde iv. Okay. Paired is false because they're not paired together. Bar.equal equals true. Okay. And that is a part of the data screening thing. So if you remember from the lecture we talked about data screening, one of the things was that they had to have homogeneity, which is that the variance between groups is equal. We're actually telling it that we know the variance is equal because we haven't gotten to data screening yet this semester. So once we get to data screening, we'll talk more about like what should I do if the variances aren't equal. But for right now, we're just going to set it to be equal so everybody gets the same answer. So dv tilde iv paired equals false, var.equal equals true. Now it should say 2 sample t-test if you've done this correctly. If you have run the wrong one, let me run dependent t example one more time, see how it says paired t-test. Now we should see 2 sample t-test. And it says that our t value it's negative, which just means that one means smaller than the other. It's 2.7 to 1, so a ratio of almost 3 to 1, which is not bad. Degrees of freedom equals 6 because we had 2 groups here. So this is where it changes a little bit. It's n-1 plus n-1. So what did I have? I had 2 groups, each with 4 people in it. So I have 8 observations. So you would think this would be n-1 and it would be 7. But that's not true. It's n-1 for each group because I had to calculate the mean for each group. And so to hold that mean consistent, I need one person in each group to be a specific number. And so that's why it's actually n-2. P-value, and so I would say this is significant. It's 0.04. So let's go over here and look how I wrote that up. I wrote out the means and standard deviations for each group. My t-value here, so t, degrees of freedom, 2.66. P equals 0.4. Okay, so I just rounded up. Now, to get our mean, standard deviations, and n, we're going to kind of set this up the same. We're going to say the mean equals dv, comma, iv. And I added this little list function here. That is a preview for later. So it will run with and without list, but it won't hurt you to add list. Right? So what does list do? Okay. It allows you to add more IVs. So if I had I wanted to split 6 different ways, I could add more variables here in the list function. And when we get to two-way ANOVAs, that will be important. So a little bit of preview here. I'm going to save those means. Here I've got my standard deviations. And I'm not using NARM, but I could. I think I didn't have it in there before because I knew I didn't have any missing data. Whoa. This is n. So let's do what we did a minute ago. Mean, STDV, and n. And so that gave me very nicely lined up all pretty the means and standard deviations for each group and the number of people in each group. And this time it is different. Right? So that's where I got these numbers from. So I do have 4 people in each group. That sets me up very nicely for d dot independent t. So I'm going to do mean 1 equals 1775. Mean, let's just go in order this time. Mean 2 equals 23.00. SD1 equals, I like to stack things. So standard deviation for the first group is 3.30. SD2 is 2.16. N1 this time, because there's 2 groups, it was 4. N2 equals 4. Okay. Alpha is 0.05. K equals 2. Now if I stack my code this way, look, it looks exactly like the output that I'm looking at. So that is what makes it a little easier to make sure you've entered the right numbers in the right places. Now I get my D value, it's negative 1.88, which that does not match over here. I must have just been cutting and pasting. Let's fix that. 88. Okay. But my T values match, 0.04, D equals 1.88. And I listed it here as positive, mostly because it doesn't really matter which way you do it. If you include the negative to make it match, stupid negative. There we go. The t-test, but let's look at our confidence interval here, which is a little hard to read because of all the negatives. So it's negative 3.5, which is huge, to negative 0.10. So the range of plausible values for this D ranges from almost 0 to very large. So I've got to be a little suspicious here because that score range is so large. This effect is pretty big. It appears that the control group who's not being hypnotized is remembering more things, right? But my effect size is a really wide range, so it could be almost anything at this point. All right, so that should be the end of t-test. And please come get help if you don't understand some of the stuff that's going on. I know at the very beginning when you're learning R, it's just like a ton of stuff at once. Like, oh my gosh, all these commands, how am I supposed to remember what order all this stuff goes in? Take notes, get help, watch this again. So don't forget to come to the help desk. Let's end this with something easy, which is correlation. Okay. So correlation, the one we're going to use requires the hmisc library. So remember, you need to install that first if you don't have it. So we're going to click install, capital H, misc, okay, and click install. Load the library, so run this line of code, which I already did, and it gave me some that was loading packages and then it's mad at me because I haven't updated my R yet. And the temptation is to take the data set, the correlation data set, and this is after you learn how to do data screening. This is when you'll be tempted to do this. It's just to do rcorr, and then, which is the function, so give me a correlation table, an R correlation table, of the entire data frame. So if you do that, it goes, bleh, I don't like that. And then it gives you this error at the bottom, which is one of the worst, where it says list object cannot be coerced into type double. Okay. That error pops up a lot and is not super helpful because it, until you kind of learn R a little better, is pretty vague for you. Okay. So what are we correlating first of all? So we're measuring femininity and sympathy. Is there a correlation between these two variables? Yes, but it's kind of small. Let's see if we can find that. So the way rcorr works, and the reason that with this double error is that it needs to have the command as.matrix. And so it specifically wants this to not be a data frame, which is the kind of data we're used to using. Instead, it wants it to be a matrix. So when you run that, we're gonna turn that stuff off because that's a different example. What you'll get here is a correlation table of your variables. So feminine to feminine are perfectly correlated because it's the same variable. And so then it gives you feminine to sympathy, which is where I got 0.18. And then feminine to sympathy again, and then the sympathy to sympathy. So it gives you the whole square, which means only look at one half of the square. Okay. It tells you the N, so how many people there are. So there's 369 people in this data set. And then our p-value down here. So it gives me the p-values for the correlations it tested. So it gave me the same p twice. If you are not good at scientific notation, this is how you turn it off. So option scipen equals 999. I don't know, it should be false, but this is what the code is. So I'm gonna run that, rerun my correlation table, and this time I can see the p-value written out. So it's less than 0.001. Which is where I got this code. Now correlation is its own effect size, so we don't have to do any special fanciness for the effect size here. And it's somewhere between medium, small and medium. Okay. We could calculate the confidence interval for this, but for right now I just want you to get how do I even get a p-value for a correlation. In data screening, we'll talk about how you can get a lot of correlations at once when you're not interested in their p-values. In a little bit simpler way, but if you're interested in is the correlation significant, rcorr is the easiest function. All right, all of that at once, that is how you do a single sample t, independent t, dependent t, and correlations in R. Like I said, if you're feeling lost, be sure you come and get help. And so now you should be able to do the basics homework.